Hi students, we're going to take a look today at plate tectonics. If you were an alien coming to Earth for the first time and you were comparing our planet to all the other planets that this highly experienced alien has seen on its travels around the universe, you would probably notice a couple things about our planet. One is its temperature, and that temperature is just right for liquid water. It's not too hot so that all the water is vapor. It's not so cold that all the water is frozen. A significant portion of the planet has liquid water, so that's water between 0 degrees Celsius and 100 degrees Celsius. And that's pretty remarkable. Obviously, that's very important for life. The other thing that would probably jump out at you as being really unusual about Earth as compared to the other planets in the neighborhood is that it has plate tectonics with two distinct types of crust. As you're looking down on the planet, you can see there are huge swaths of the Earth that poke up above sea level, and they're all just a little bit above sea level relative to how far below sea level the oceans go. And then the oceans are floored by a dramatically different kind of crust. And if you watched over the long term, you would see the continents moving around, the oceanic crust being generated and destroyed. So these are distinctive things about our planet, and they're both actually really important for keeping the surface of the planet fresh and viable for life. So let's compare those two types of crust. We've got continental crust and oceanic crust. Continental crust is thicker, it's overall granitic in its composition, and has a density of around 2.65 to 2.7 grams per cubic centimeter. The oceanic crust, in contrast, is much thinner, it's overall basaltic in its composition, and it's got an average density of around 2.9 grams per cubic centimeter. So this is part of the picture when it comes to plates. The continental crust is something like the cork that you see here in this part of the picture, where you've got relatively lightweight stuff floating on the water. The oceanic crust is more like the pine over here, which is a little bit more dense, but not nearly as dense as the oak you see below both of them. That oak is essentially the mantle that's part of the plates, the lithospheric mantle that's stuck to the bottom of the crust. The oceanic crust has a little less mantle underneath it. The continental crust has a little bit more. But together, those things make up the bulk of the plate thickness. So plate tectonics goes to two ideas in terms of its origin, the idea of continental drift and the idea of seafloor spreading. We'll start with continental drift. This is Alfred Wegener. Alfred Wegener was a German meteorologist who studied the weather, and he was also full of some very bright ideas about other stuff in the Earth system. So specifically, he noticed that the edge of South America and the edge of Africa looked like they would fit together very well. And this led him to develop this idea called Pangea, the idea that all the continents were connected together in the past. This is a modern-day reconstruction of Pangea. Wegener's reconstruction looked a little different. But you can see here how nicely all the continents fit together. It's pretty pronounced. So Wegener had several lines of evidence for his proposal that the continents had drifted away from this original Pangea starting point. His first line of evidence was the shape of the continents. So that's what's being illustrated here. South America and Africa fit together very, very snugly when you consider the edge of the continental crust of each. So South Africa's coast is not necessarily where its continental crust stops. You can see the continental crust extends some distance beyond the coast. It's a shallow ocean there, not nearly as deep as the ocean where you've got oceanic crust below it. Another thing that Wegener looked at, his second line of evidence, was modern mountain belts. So these are landforms that, for instance, in the United States, we call the Appalachian Mountains. They call them the Caledonides up in Scandinavia. There are similar mountainous rocks in Newfoundland, Scotland, Ireland, and even in Greenland. And even in Africa, underneath the sands of the Sahara, there are similar mountain rocks. So Wegener said this could be 6 different mountain belts, or if you remove the Atlantic Ocean, they all fit together nice and neatly, and they appear to be just modern-day scraps of a single ancestral mountain belt. Wegener also went back further in time and looked at ancient mountain belts. And so these are really old mountain belts. You can see here they're Proterozoic in age, which means that they're basically about 2.5 billion years old to 500 million years old. And these Proterozoic mountain belts wrap around little chunks of even older crust. These are little continental nuclei that existed during the Archean. basically from 3,800 to 2,500 million years ago. So you can see these Archean blocks of crust here as the green bits, and then you can see these Proterozoic mountain belts wrapping around them and basically trailing off the edge of South America and picking up again on the edge of Africa. Pretty remarkable fit here between the structures on either side of that break. Wegener was a meteorologist, so he was interested in the effects of weather on these continents. And one of the principal controls on weather in the modern world is latitude. So it's warmest at our equator, it's coldest at our poles, and of course you and I live in the temperate mid-latitudes where it's middle range temperature. There are also some latitudes, the subtropical highs, they call them, where high pressure air descends from the atmosphere, and basically it's very low in moisture, so it causes deserts. So Wegener knew that that pattern existed in the modern world, and he looked for it at the time of Pangaea. So he went and he looked at late Paleozoic age rocks. These are Pennsylvanian and Permian age rocks. And he found that there was a big signature of glaciation in what he interpreted to be the polar region of Pangaea. These were glacial sediments, glaciogenic sediments, sediments that were made by glaciers. And they showed up in southern South America and southern Africa, in India, in Australia, and Antarctica. And then he found a band of desert sediments and then a band of what he interpreted to be tropical sediments. These were basically very rich in plant matter, so these were coal deposits, and he interpreted that to be reflective of the ancestral equator. And then he found another band of desert sediments above that. So these were, dunes, sandstones, and things like that from deserts. So he interpreted that pattern as reflecting the paleo latitudes, the paleo equator, and the paleo poles of the Earth at the time of Pangaea. So these are sedimentary rocks, but they're basically reflecting ancient climate. So we can go into a little bit more detail here on one subset of that. So we can call this 4B, if you want. The glacial sediments, he interpreted there as having been an ice cap over the South Pole, over Antarctica. Antarctica was then over the South Pole as it is today. So this is a little confusing because Antarctica has actually shifted around a bit, but it happens to be back roughly where it was then. But as that ice mass built up, it flowed out in all directions from the center of the ice cap. And we can see this pattern happening today in Antarctica or in Greenland, or even in small little ice caps that we see in places like Alaska or Iceland. And so there's this radial pattern of flow, and that ends up being recorded by scratches in the rocks. As glaciers flow over the land, they carry boulders and cobbles that scratch the bedrock that they flow over. And those scratches are preserved in the geologic record. So if you go to South America today, you've got scratches that basically show that pattern. And if you go to South Africa today, you've got scratches that show that pattern. India, it looks like this. Australia, you can see it looks something like that. And if you reconstruct those all back to where Wegener thought they were, then it makes a nice radial pattern like the spokes on a bicycle wheel. So Wegener put that forward as another line of evidence. Finally, he examined some fossil evidence, and these are two fossil organisms, a plant on the left and an animal on the right. Glossopteris is a Paleozoic seed fern, and Mesosaurus is a small freshwater reptile. So this is not a reptile that lived in the oceans, it lived in freshwater lakes and streams. You can see here from the scale bar, Mesosaurus was not as big as something like a dinosaur. This was only a few inches long. Well, it turns out that you can find these fossils in interesting places. So, for instance, let's examine where we find Mesosaurus fossils. We find them today in both Central Africa and Central South America and nowhere else on the planet. So Wegener said there's one way you can explain that by saying there were these two independent populations separated by an ocean, or maybe this was one continuous population that then later was broken up by continental drift as Africa moved away from South America. Similarly, we can look at a bunch of other species like Lystrosaurus here. Lystrosaurus fossils are found in Africa, India, and Antarctica. We can look at the Glossopteris seed ferns, which are found in this belt here. And another critter over here, Cynognathus, is found in southern South America and southern South Africa. This pattern of fossil evidence suggested that the continents had been connected in the past too. So Alfred Wegener put forward those ideas about continental drift, but they didn't immediately take hold. A missing piece of the picture for Wegener was what was happening in the oceans. And the oceanic side of the story wasn't revealed until the aftermath of World War II. Now I've got a picture of a nuclear submarine on here, but in World War II there were many battles that were fought at sea by submarines. And these submarines were a major force in the conflict between nations. The United States Navy spent a lot of money and effort mapping the seafloor, motivated by the question of where we could stash our submarines, where the Germans wouldn't find them, and where the Germans might try and stash their submarines so we could find them. After the conflict was over and the world was at peace again, that information was revealed to the world, and it turned out to have some very interesting stuff going on. The shape of the seafloor was one of the first things that was revealed, that was itself so extraordinary that it motivated additional study of the seafloor, which revealed information about paleomagnetic signatures and the age of the oceanic crust. And those three things all went together to give us this second big idea, which is the idea of seafloor spreading. So the seafloor was mapped using sonar. Sonar is basically like echolocation. It uses sound waves, little compressional waves that travel through the water, bounce off the bottom, and come back up to be heard by a ship. Nowadays we can do this in very focused little beams called multi-beam sonar, and we can even do this with little robots that are towed over the seafloor, and we can get a really detailed picture. So it can result in a picture of the seafloor that is almost as detailed as the topographic images that we have of the land. So what did we find? It turns out that the longest range of mountains on the planet Earth is hidden at the bottom of the sea. It's called the Oceanic Ridge System. This is a picture showing a portion of the Oceanic Ridge System, the Mid-Atlantic Ridge, which is midway through the Atlantic Ocean. So this is pretty striking because it's about the same distance from the North American continent to the Mid-Atlantic Ridge as it is from the African continent to the Mid-Atlantic Ridge. So there's the continental margin, which is the continental crust that's basically flooded by seawater, and then there's this deep ocean basin, and then there's this Mid-Atlantic Ridge, and right at the very summit there's a little notch in it. And that notch is thought to be significant. We'll examine why in just a second. Zooming out a bit here to take a look at the bigger picture of the topography of the seafloor, you can see that we were just examining this region here, but you can see that that oceanic ridge system wraps around the world kind of like the seams wrap around a baseball. And it's not the only striking feature. There are also these really deep zones, these long furrows called trenches that can be found in certain regions of the world, and these trenches also seem to tell an interesting story. These observations led to the formulation of an idea called seafloor spreading. Seafloor spreading was promulgated by the scientist you see in the lower right there, a former naval officer, Harry Hess, who worked at Princeton. The idea here is that new seafloor is generated by upwelling of the mantle underneath these ridge zones. And so as they spread apart from one another, then you end up basically creating a gap between them. And that gap is filled in by little intrusions of new magma. So there's a little bit of magma that's generated here by this upwelling mantle, and it seeps into those cracks and seals them shut, and that makes new oceanic crust. So the seafloor there is spreading. It's widening over time. And one way to think about that is to think of like South America and Africa as being two ships sailing away from one another in a cold ocean, and then ice forming in the wake of those two mutually departing ships. So the further they spread apart, they open up this gap between them. They develop this little skirt of ice on the tailing edge of the ship, and then that ice basically cracks open, fresh water seeps into the crack and seals it shut over and over and over again. But if that was the only part of the story, then the planet Earth will be swelling up like a balloon. So that's not the only part of the story. We also see that in other places, oceanic crust is destroyed at so-called subduction zones. So a nice example of a subduction zone is on the west coast of South America, where you can see there's oceanic lithosphere, the oceanic crust plus the underlying mantle, that's heading back down into the lower mantle. That is what's manifested at the surface as that deep furrow called a trench. And as it turns out, those trenches are parallel to chains of volcanoes, continental volcanic arcs or oceanic island arcs. So we've got this overall sense of motion in the mantle where it's rising in one area and sinking in another area that creates basically a loop sort of shape. And so a series of these mantle currents, these loops, give us the driving force for this seafloor spreading. And meanwhile, incidentally, the continents are drifting around. So when you take seafloor spreading and you put it together with continental drift, you end up with the big idea here, which is plate tectonics. Now, I mentioned paleomagnetism, magnetic signatures that are preserved in the rocks, so let me say a little bit more about that. The Earth basically acts like a giant bar magnet, which has a North Pole and a South Pole. Now, you know that our geographic North Pole is up, sort of at the spot where the Earth's axis of spin emerges from the planet's surface. But the magnetic North Pole is off a little bit from that. Lines of magnetic force emanate from the planet's South Pole, wrap around the planet in space, and then come back in again at the magnetic North Pole. This is really important because the shape of the magnetic field ends up imparting very specific characteristics to the rocks. You'll notice that the magnetic field is almost vertical in these polar regions, all right, whether we're at the North Pole where it's poking in or at the South Pole where it's poking out. But it's almost horizontal here at the equatorial regions. It looks really different relative to the surface of the Earth than what we see in the polar regions. The actual shape of the Earth's magnetic field isn't a perfect little donut shape like that. It's actually distorted by the force of the solar wind. The solar wind is a constant stream of charged particles that comes off the sun, and it basically slams into the Earth and distorts the shape of our magnetic field, squashing it on the side that's facing the sun and stretching it out in the direction that is downwind of the sun. That doesn't really change what's happening right here at the surface of the Earth, though, but I wanted to point out that further out it has a different shape than the one I just depicted. How does this matter for rocks? Well, rocks can, in some cases, take on the Earth's magnetic signature at the time they form. To do this, you need to have either loose particles in a sedimentary rock that are settling down at the bottom of the sea, so you've got some little flakes of clay and flakes of magnetite that are settling down and making layers on the seafloor. And those will line themselves up with the Earth's magnetic field so that if this eventually turns into a sedimentary rock, it will bear that magnetic signature. The other possibility is that you could have a volcano, and as that volcano erupts some lava, there are crystals in that lava that might be magnetically susceptible. They will line themselves up within the soup of the lava with the Earth's magnetic field. Once that lava is congealed into igneous rock, that magnetic signature is locked in. So we can sample ancient lavas and we can sample sedimentary rocks and we can tease out their magnetic signature. There are two aspects of this magnetic signature we pay attention to. One is its declination. The other is its inclination. So declination, it occurs within the horizontal plane, and it's basically relative to the directions on the compass, relative to due north. So for example, northeast is an example of declination, or east is an example of declination. East is 90 degrees away from north. Inclination is how tilted it is relative to the horizontal. So if this surface on this diagram is horizontal, then this surface here is vertical. A fossil magnet, a little magnetic grain within a sedimentary rock or a lava flow can have a direction of plunge into the Earth's interior. And that could be perfectly horizontal, or it could be kind of steep, or it could be perfectly vertical. So if it were forming today at the South Pole, we'd expect it to be vertical pointing up. If it were forming today at the North Pole, we'd expect it to be vertical pointing down. If it were forming today at the equator, we'd expect it to be horizontal, and at mid-latitudes, we'd expect it to have inclinations somewhere in between vertical and horizontal. Here's a look at that. At the magnetic equator, fossil magnets would be horizontal. At the magnetic North Pole, they'd be vertical. And at intermediate latitudes, like the one we live at, they'd have some inclination. We live at about 38 degrees latitude here in Annandale, Virginia, so that works out to a magnetic inclination of around 57 degrees or so. So if we're looking at a vertical plane through a rock here, where this is 0 and this is 90, 57 will be something like that. We can go and we can sample rocks of different ages and read their magnetic signatures, and this tells us something interesting. So here's an example, a situation where you've got some folded Cambrian age sediments that have been eroded and overlain by a relatively young Quaternary aged lava. The magnetic signature in the lava matches the Earth's present-day magnetic field. But the magnetic signature in the Cambrian sediments does not match the Earth's present-day magnetic field, and it doesn't even match, other parts of that same sedimentary package. So in order to make this make sense, we've got to mentally unfold those Cambrian age sediments so they look like the example over here on the right. Once unfolded, the angle of inclination for each of the little magnetic grains is constant relative to the bedding in which it's contained. And that basically tells us what the Cambrian magnetic field's orientation was. All right, so here it's a moderate orientation. That would correspond to a relatively equatorial latitude relative to the high angle that we see in the modern day present field. Some examples of how this works. Over here on the left diagram, we've got rocks that are forming today at location number 1 and location number 2 and location number 3. You can see how their little magnetic arrow is oriented parallel to the overall shape of the Earth's magnetic field. So it's pointing out here in this southerly latitude, it's pointing in this northerly latitude, and here at this equatorial latitude, it's more or less horizontal. So if we go and we find some rocks like are shown here in this second picture, so rocks that are called Y and X and Z, and we look at their magnetic signatures, we can actually figure out what latitude they formed at relative to the Earth's magnetic field by lining those arrows back up with the Earth's magnetic field. So X, which starts off here in the modern day, would have to be reconstructed to a past position when it formed down here near the South Pole. Z is near the South Pole today and Y is near the North Pole, but in order for their relatively horizontal orientations to make sense, we're going to need to restore them near the equator at the time they formed. So this allows us, for any given package of rocks on a given continent, say, to reconstruct their position relative to the magnetic North Pole over time. So here you've got a stack of sedimentary layers. Those sedimentary layers have magnetic signatures in them. And by using those magnetic signatures, we can say that for this continent's sort of biography, its perspective, 600 million years ago, the North Pole was here. 500 million years ago, it had moved to here. 300 million or 400 million years ago, it was here. 300 million years ago, here. 200, 100, and 0 million years ago, it happened to be right here at the North Pole where we find it today. So this is called apparent polar wander, all right? It's not true polar wander because the true pole is actually staying more or less in the same spot, and it's the continent itself that's moving, not the pole. And we know this because when we go and we talk to different continents and we stack up their stories of where the pole has gone relative to them, we find that they don't agree with one another. So the European apparent polar wander path is different from the South American apparent polar wander path, is different from Africa, is different from India, is different from Australia, is different from North America. What they all agree on is that nowadays the North Pole is at the North Pole. But they all start off in different positions relative to that as you go further back in time. So this apparent polar wander can be understood by allowing the continents to move. So if, for instance, on continent A, you look at rocks that are 200 million years old, and on continent B, you look at rocks that are 200 million years old, and you ask them, where was the North Pole 200 million years ago? Continent B gives you a different answer from continent A. And what you can do to reconcile those two answers is to remove the intervening ocean basin and restore the continental edges of A and B, and you'll find that, say, they both point to the same position. The continents, in other words, move. Not only that, but the oceans have a magnetic story to tell as well. And this is told in the form of magnetic reversals. So it turns out that the Earth's magnetic field is not actually stable over the geological long term. It flips back and forth. And when it flips, the North Pole becomes the South Pole and the South Pole becomes the North Pole. You wouldn't notice this just walking around on a daily basis. It's not like suddenly, day becomes night and night becomes day. It's just that the orientation of flow within the Earth's magnetic field flows in the opposite direction. So we talked about how, the Earth's magnetic field today basically emanates from the South Pole and comes back into the North Pole. During a time of reversal, it flows out of the North Pole and comes back in at the South Pole. But in both those polar regions, it's still going to be high angle orientation relative to the Earth's surface, and still in the equators, it's going to be low angle. The difference is basically which way it's pointing. So, in a series of really foundational studies of the Valles caldera in New Mexico, scientists looked at the different layers that make up the side of that volcano. And they found that 1.2 million years ago, it has a magnetic orientation that basically matches the modern day field. But at 800,000 years ago, 0.8 million years ago, it's reversed. So it's got the same angle, but it's pointing up rather than pointing down. And then by 400,000 years ago, it's turned back to pointing down again. So these are reversals of the Earth's magnetic field recorded in this sequence of volcanic layers. And using this sort of information, paleomagneticists, the geologists who study paleomagnetism, or as they like to refer to themselves, paleomagicians, they go and they've worked out a geologic timescale that's based on these magnetic reversals. Right now we're in the Brunei's normal chron, this segment when the magnetic field is normal, and by normal we mean it's like what we have today. But previous to that there was a reversed chron, and previous to that there was a normal chron, and then there was a bigger reversed chron. That one's called the Matuyama reversed chron. And then there was a normal one, and a reversed one, and a normal one, and a reversed one that was very short, and a normal one, and a reversed one, and so on. In the past 4 million years, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9 reversals of the Earth's magnetic field. So this thing flips back and forth pretty regularly over geological timescales. What does this mean in terms of the ocean basins? Well, if the Earth's magnetic field is flipping back and forth over time and the seafloor is spreading, then the seafloor is made out of lava, then the seafloor should record changes in the Earth's magnetic field through time. This is a screenshot of Google Earth, and you can see a little bit of the top of Greenland here and a little bit of the top of Svalbard. But most of the planet's surface here is covered up with a magnetic signature map. I'll point out a couple things here. Here's the rest of Greenland, kind of coming down like this. Here's Iceland, and here's Scandinavia. Britain and Ireland are here, and here's the edge of North America over there. So this is the Atlantic Ocean running basically right down here through the middle of Iceland, and you'll see there are some little stripes there. Do you see those stripes in the Earth's magnetic field on either side of the mid-Atlantic ridge? Those stripes are these magnetic signatures that are preserved in the oceanic crust, and they're basically the same on either side of the mid-Atlantic ridge. Here's another example. This is the Juan de Fuca Ridge off the coast of Washington State. So this is the ridge between the Pacific Plate and the Juan de Fuca Plate, and then there's a subduction zone here, and then this is the North American Plate over on the far right. So there's 3 plates in this picture. But as the Juan de Fuca Plate and the Pacific Plate separate from one another along this ridge, the crust takes on the magnetic signature of the Earth at the time it forms. And so we end up with a color-coded scale here showing the age and the orientation of the magnetic field. The key thing that I want you to realize here is that the west half looks like the mirror image of the east half. So this is sort of like a 2-directional tape recorder that is keeping a record of the Earth's magnetic field as the seafloor is spreading. Here's a diagram sort of showing how this would work over time. 2 continents separate, call them, say, North America and Africa, and as they separate, oceanic crust and oceanic lithosphere is generated in the wake between them. If the Earth's magnetic field is normal, then that crust takes on a magnetically normal orientation. If the magnetic field is reversed, then it takes on a reversed orientation, this sort of red color. If it flips back to normal again, then the seafloor keeps on spreading, but this time it's taking on a normal orientation. The changes in the magnetic field don't cause seafloor spreading, but they're sort of passively recorded by seafloor spreading. And this pattern of magnetic stripes was sort of the thing that really sealed the deal in a lot of geoscientists' minds about the reality of seafloor spreading. Okay, one other insight that we had motivated by this extraordinary topography that was discovered after World War II on the seafloor was oceanic ships went out and they started coring the seafloor. Coring means they would go and take samples of the seafloor that are in the shape of cores, so they're like cylindrical samples down through the sediments on the seafloor. And those sediments contain fossils, and those fossils tell us the age of the seafloor. And a fascinating pattern emerged that basically exactly mirrored the topography of the seafloor, and that is the pattern shown in this picture. This shows the age of the oceanic crust, and you'll see that the oldest oceanic crust is nowhere more than about 150 million years old. It's sort of a blue color, so blue represents kind of older ages on this map. And then the younger colors are the reds and oranges and yellows, and gray is the very youngest of all. And you can see that that basically plots exactly on top of those oceanic ridge systems. So that's where we find the very youngest crust. Furthermore, you can see that the Mid-Atlantic ridge is not spreading quite as fast as the oceanic ridge system in the Indian Ocean, and even that pales in comparison to the East Pacific rise, which is spreading at the most vigorous rate. So not all ocean basins are created equal here. Some spread more rapidly than others. Of course, the Pacific is not getting wider than the other ocean basins because of those subduction zones that we talked about earlier that are basically taking that old oceanic crust and shoving it down back into the mantle again. So the age of the oceanic crust is youngest at the oceanic ridges, and it gets older further away from those. So we arrive at our final idea here, this plate tectonics idea. The idea succinctly expressed would be this. The outermost rocky surface of the world is broken into a series of pieces or chunks. We call these plates. Exactly how many there are, it's kind of hard to count. I think a reasonable count would be on the order of about a dozen or 14. Some of them are quite big, like the Pacific plate, the Eurasian plate, the North American plate. Some are pretty petite. The Caribbean plate, the Cocos plate, the Juan de Fuca, the Iran plate, the Philippine plate are all pretty small. But these pieces move around relative to one another, and there are three different ways that they move relative to one another. They either move toward one another, away from one another, or slide past one another. All right, and those three types of plate boundaries end up determining everything that matters in terms of the local scenario. So when they converge, you end up getting mountain building. When they diverge, you get new ocean basins and rifting. And when they just scrape past each other, you get a lot of earthquakes, but not much else. So we're going to examine those different kinds of plate boundaries next. As a quick summary of what we've talked about in this presentation, we talked about Alfred Wegener's idea of continental drift and his multiple lines of evidence for continental drift. And then after World War II, additional evidence that was added for this idea called seafloor spreading. And we indicated that there were three main kinds of evidence for seafloor spreading. First among those was the shape of the seafloor, and then subsequent scientific investigation revealed the paleomagnetic reversals and the age of the oceanic crust. And then we end up with this big sort of take-home message, which is plate tectonics, an idea that has resulted from combining these ideas of continental drift and seafloor spreading. So I hope that is a useful summary of the chain of thinking and evidence that got us to the idea of plate tectonics. Next up, we'll explore the plate boundaries.